Hello everyone and welcome to the lecture on Amazon EMR, Elastic MapReduce. So, what is Elastic MapReduce or EMR? Elastic MapReduce or EMR is a cloud-native big data platform allowing for the processing of vast amounts of data across resizable clusters of Amazon EC2 instances. In simpler terms, it takes care of setting up, managing and scaling of a collection of virtual machines for you. Hadoop ecosystem, it provides access to various big data platforms such as Apache Hadoop, Spark, HBase. EMR is essentially an implementation of these big data frameworks and others and making it easier to run and manage them. Scalability. One of the key features of EMR is its ability to automatically scale resources as needed. This ensures that the cluster has enough capacity for the task it is performing while keeping cost in check. Data processing. It's commonly used for data processing tasks like batch processing, stream processing, machine learning, and even scientific simulation. This versatility makes it suitable for a variety of data engineering and data science tasks. AWS service. Elastic MapReduce is an AWS offering, and this means it is integrated with other AWS services like S3 for storage and Identity and Access Management for security, which can make it easier to implement in an AWS-centric environment. Okay, next I'll just briefly talk about Hadoop because EMR is basically Hadoop services, Apache Spark and some other components, but Hadoop is important. So just to know about Hadoop will be good. So open source framework. Hadoop is an open source framework initially developed by Doug Cutting and Mike Caffarella, and it is now managed by Apache Software Foundation. Its primary goal is to facilitate the processing and storage of large data sets. Distributed computing. Hadoop enables distributed computing by dividing tasks and data across multiple computers known as nodes, and this parallel processing increases efficiency and allows for handling of massive data sets. HDFS storage. Hadoop Distributed File System is the storage component of Hadoop. It stores files in a distributed manner, providing high availability and fault tolerance. MapReduce engine. MapReduce is the data processing engine in Hadoop. It consists of two primary functions: map, which filters and sorts data, and reduce, which performs calculations and transformations. Ecosystem components. Hadoop's ecosystem includes various tools and libraries like Hive, Pig, HBase and Yarn, which extend its capabilities in areas like data warehousing, scripting, database management and resource scheduling. Next, I will just briefly talk something about Apache Spark. So, general purpose computing engine. Apache Spark is an open source distributed computing system designed for big data processing and analytics. Developed by Apache Software Foundation, it provides an alternative to Hadoop's MapReduce component. In-memory processing. Unlike Hadoop, which relies on disk storage and data processing, Spark stores data in memory. This accelerates data processing speeds, making Spark suitable for real-time analytics and iterative algorithms. Data processing libraries. Spark comes with a variety of built-in libraries for tasks such as machine learning, and that library is MLlib, graph processing, library name is GraphX, and stream analytics, Spark streaming library. Spark ecosystem. Spark's ecosystem includes additional components like Spark SQL for SQL queries and Spark R for R programming language integration and Delta Lake for reliable data lakes. Fault tolerance. Spark ensures fault tolerance through data replication and lineage information, allowing it to recover lost data and continue operations in the event of a node failure. So, coming back to Elastic MapReduce architecture, EMR architecture. Cluster manager. Elastic MapReduce uses a cluster manager to oversee the resource allocation and job execution within the cluster. The cluster manager can be either Yarn, which is yet another resource negotiator, or Mesos, but Yarn is most commonly used. Data storage. EMR primarily uses Amazon S3 as data storage layer. However, it can also utilize HDFS for data storage within the cluster. Now, compute nodes. The architecture is made up of different types of nodes, namely master, core, and task nodes. The master node controls job tracking, core nodes store data and run tasks, and task nodes only run tasks. EMR components. Elastic MapReduce comes packed with multiple components like Hadoop, Hive, Spark, HBase, providing a comprehensive big data platform. And data processing framework. EMR supports various data processing frameworks like we have already talked about: Spark, Flink, Apache Spark, Apache Flink. So now we'll just go a bit deeper into the types of nodes or the roles of nodes in EMR. First one is master node. The master node in an EMR cluster is responsible for managing the overall cluster coordination and job orchestration. It runs the name node service for the HDFS and resource manager service for the yarn. The master node ensures that jobs are scheduled appropriately and that resources are allocated effectively. Core node. Core nodes store data and handle data processing tasks. They run both the data node service for HDFS and node manager service for yarn. Core nodes are essential for running tasks and storing data blocks. Task node. Task nodes are optional and are used solely for data processing. They only run the node manager service for yarn. These nodes do not store any data but provides additional computational capacity for running tasks. Okay, now I'll just talk something about, there are two types of cluster. One is transient and long running clusters. So first one is transient clusters. These transient clusters are short-lived EMR clusters designed for specific tasks. They are terminated once the job or workflow completes, resulting in a cost-effective solution for one-time data processing tasks. Next is long-running clusters. These clusters are persistent and remain active for an extended period. They are ideal for applications requiring continuous data ingestion, transformation, and processing. Some use cases. Transient clusters are usually used for batch processing tasks like ETL, extract, transform, load, or data analytics. Long-running clusters are more suited for real-time data analytics and stream processing. Cost implications. Transient clusters can be more cost-effective as they exist only for the duration of specific tasks. Long-running clusters, however, incur cost as long as they remain active. Data persistence. In transient cluster, data is often stored in Amazon S3 to ensure persistence after termination. But in long-running clusters, long-running cluster may use HDFS also for longer data retention within the cluster. So it's up to you. Long-running clusters can also use HDFS or S3 both. But for transient cluster, we will be using mostly S3 because they will come and go, and we don't want to lose data. So next is something about EMR integrations. So first one is Amazon S3. EMR is often integrated with Amazon S3 for scalable data storage. You can use S3 buckets as data input and output locations for your EMR cluster, thereby enabling better data persistence and easy access. Next is AWS Lambda. Lambda functions can be used to trigger EMR jobs based on specific events like changes in an S3 bucket, and this enables real-time processing and automation of workflows. Amazon RDS. Amazon RDS databases can be directly queried using EMR cluster for analytic tasks. This creates a seamless flow between transactional and analytical data processing. Amazon EC2. EMR clusters are built on EC2 instances, which provide the computational resources. You can select different EC2 instance types based on your specific needs, optimizing for memory, CPU, or other factors. AWS Glue. AWS Glue can be used for cataloging data sources, which makes data readily accessible and queryable for EMR. It also simplifies ETL processes. AWS CloudWatch. Integration with CloudWatch allows you to monitor the performance and health of your EMR clusters in real time. Alerts can be set up for specific metrics or events. Next is storage options in Amazon EMR. First is HDFS. HDFS is the native storage system designed to work seamlessly with Hadoop application. It is good for large streaming reads and is generally optimized for throughput rather than latency. Next is Amazon S3. So S3 offers highly durable and available object storage. It is often used for persistent storage beyond the life cycle of an EMR cluster. One of its primary advantages is decoupling storage from compute resources. Third is local file system. Local storage is ephemeral and exists only for the duration of the cluster. This is suitable for temporary storage needs or for use as a scratch space for intermediate data. Finally, EMRFS, which is Amazon EMR file system. EMRFS is an extension for EMR that allows direct and performant integration with S3. It allows for features like data consistency and S3 server-side and client-side encryption. Next is scalability, fault tolerance and high availability features in Amazon EMR. First one, horizontal scaling. Amazon EMR allows you to add or remove instances to your cluster to manage the workload effectively. This is often done through elastic MapReduce auto scaling feature, which adjusts the number of instances based on real-time demand. Vertical scaling. Vertical scaling involves increasing the size of individual instances to provide more computing power. However, this approach is generally less flexible than horizontal scaling and might require manual intervention. Data replication in HDFS. EMR's native HDFS has built-in fault tolerance by replicating data across multiple nodes. This ensures data availability even if a node or several nodes fail. Auto recovery features. Amazon EMR is designed to recover automatically from failures. For example, if a data node fails, EMR will redistribute the workloads to other nodes in the cluster, ensuring that your operations continue smoothly. Multi-AZ deployments. Amazon EMR allows for deployments across multiple availability zones, providing high availability for your data and applications. This geographical distribution safeguards against localized failures. Okay, next is automatic and managed scaling in Amazon EMR. EMR auto scaling. EMR auto scaling adjusts the size of your cluster in response to workloads. By scaling out, which is adding instances, or scaling in, which is for removing instances, auto scaling ensures optimal resource usage and minimize cost. Instance groups. Amazon EMR clusters are composed of multiple instance groups like master, core and task groups. Each of these groups can be configured to use auto scaling, which allows for a fine-grained control over cluster resources. Scaling policies. EMR auto scaling uses scaling policies which define conditions and thresholds that trigger scaling actions. You can configure these policies to react to specific Amazon CloudWatch metrics like CPU utilization or data throughput. CloudWatch metrics. Amazon CloudWatch metrics are used to monitor the cluster's performance. These metrics are what scaling policies use to decide when to scale in or out. CloudWatch integrates seamlessly with EMR, providing real-time monitoring and alarms. EMR managed scaling. This is a newer feature that automatically resizes your cluster for best performance at the lowest possible cost. Unlike EMR auto scaling, which requires user-defined policies, managed scaling automatically adjusts instance types and counts based on the workload. And that's all. Thanks for watching.